When we think about the capabilities and limitations of AI systems, we often have some idea of the kind of intelligence that we're measuring them against. Demis Hassabis talks about the human brain as an example of how something like reinforcement learning achieves general intelligence. But humans are only one kind of cognitive system, and we navigate just one sort of space. Professor Michael Levin, a distinguished professor at Tufts University, thinks that our anthropocentric conceptions of intelligence are limiting. Intelligence also exists in transcription space, in linguistic space, in ways that you and I can't conceptualize directly because we can't experience them. This broader way of thinking about intelligence and cognitive capacity sheds new light on how we might consider what it is to be a self, about the possibilities for artificially intelligent systems, and more. Adam Goldstein, a visiting scientist at Professor Levin's lab and a very accomplished technologist, thinks that some of these ideas have incredible potential for regenerative medicine and in commercial applications. I spoke with Adam and Professor Levin about their views on intelligence, how they think about AI's goals, and what the future of medicine might look like. This is the Gradient Podcast, and I am your host, Daniel Bashir. If you enjoy these episodes, you can follow us wherever you're listening to this podcast episode. You can also follow us on Substack to get regular notifications whenever we release a new article, newsletter, or podcast episode. You can also find our online magazine at thegradient.pub, where we regularly publish essays by the sorts of people I interview on the podcast. And finally, if you enjoy the episode, it would mean a great deal to us all if you'd consider leaving us a review on whatever podcast player you're using to listen to this episode. It helps more listeners like you find what we're doing, and helps us bring in more interesting guests for you to listen to. But now, without further ado, Adam Goldstein and Michael Levin. Adam and Professor Levin, I know that you two have been working together recently on some really interesting research in regenerative medicine. And I wanted to focus this conversation today, though, on, I think, a slew of things. Really, as you've mentioned, Professor Levin, the kind of unifying thread here is this idea of diverse, unconventional intelligence. And for, I think, my purposes and the purpose of this podcast, I do want to spend a lot of time on that topic itself, but also kind of bring that forward to how we start thinking about AI in those terms. Before we begin all of that, though, I'd love to hear a little bit about each of your backgrounds and how you began working together.
Okay, so let's see. My background, originally, I was a software guy. I was a coder for some years. I went to undergrad for computer science, wanted to do artificial intelligence, always interested in biology, and in particular, developmental biology, because, well, we could talk about why, but just this idea that it's the one example we have where you start off as a little blob of physics and chemistry, this little unfertilized oocyte, and eventually you become a complex metacognitive mind, at least in the case of humans. And so that transition always seemed really important to me and really foundational to understanding anything we were going to do in AI and so on. And so I got degrees in computer science and biology in undergrad. I then went to grad school for genetics. Basic developmental genetics, and then I did a postdoc in cell biology, and then I started my own lab in 2000. And since then, we've basically been doing research at the intersection of these three fields, which is biology and biophysics in particular, computer science, and behavioral science.
I'm much later to the game, so like Mike, I started as a programmer. I studied EECS at MIT as well as mechanical engineering. And then I jumped off the day after I graduated and started a travel software company. It's called Hipmunk. It's a competitor to Kayak and sites like that. And went through this sort of Silicon Valley regular thing, raised a lot of money, more than $50 million, and ultimately sold the company to SAP, a big German software company. And after I sold it, I had some time on my hands and I started to read about this new world of biology, which was very different than what I'd been taught. I learned that genes were the cause of everything. I think, like a lot of people, that was sort of planted in my mind from an early age. But as I started to read some of the more contemporary research and some of Mike's work, I realized that what was happening between cells was at least as important as what was happening within cells. That there was this whole layer of the system that just hadn't really been talked about much when I took undergrad bio, and it was way more interesting to me because it let me use some of those same models and concepts from signal processing and control theory and communication and so on. So I got hooked. I read a bunch of Mike's work. I reached out to him and I said, Mike, I think one, what you're doing is amazing and I'd like to learn from you. Two, I think what you're doing has a lot of commercial potential. And as an entrepreneur, I'd love to help you turn these into companies that could actually benefit people. So I kind of did both. So I joined Mike's lab as a visiting scientist. And then we also kicked off this project called Astonishing Labs, along with my co-founder, Jess Ma. And the three of us have put together now several companies based on the work coming out of Mike's lab. So I like to translate between the CS and the bio, and also between the bio and the company side, because it's a fun way to play at the intersection.
That's really interesting. And right now, it seems with a lot of the advancements in bio ML, a lot of people are pretty excited about ways that those things can be turned into companies. And I do definitely want to hear more a little bit later about how you, Adam, are thinking about some of those aspects of this. But maybe as a place to begin, we've kind of teased a lot of these really cool ideas that I think are going to come up in the conversation about how intelligence, how the way that things work at different sort of levels in people and metacognitive systems are a little bit different from how many people might intuit or think about them right now. So maybe just as like a brief primer, could either of you two maybe begin to explain a little bit of how you think about, well, we're interested, let's maybe bring this kind of from the AI perspective. I'm a person who is interested in developing an intelligent system, and maybe my kind of mindset around that is very much what AI people are doing today, that language is super important, that I can train reinforcement learning agents, and that the brain is maybe a proof point of how reinforcement learning works. But as Professor Levin, you've kind of noted in a lot of your works, the picture is a lot more complicated than that. There are sort of multiple different levels of competencies that come into play. So could you tell me just a little bit, very broadly, how you think about the idea of the way people work when it comes to intelligence, goal directedness, accomplishing tasks?
Yeah. I think a good place to start is with this idea that we as humans have evolved with a very specific and very narrow set of skills for recognizing intelligence. So we are pretty good, and not even great, but pretty good at recognizing intelligence of, let's say, medium-sized objects moving at medium speeds through three-dimensional space. So we look at primates, and we look at certain kinds of birds, and maybe an octopus and things like that, and we can recognize what's obvious to us as intelligent behavior. But we really have a lot of problems recognizing these things in unconventional embodiments. So things that are extremely large or extremely small or very slow or very fast, different spatial and temporal scales. And we, furthermore, all of our sense organs point outwards. And we also have a lot of trouble detecting intelligent behavior in unfamiliar spaces. So, for example, I think that if we had evolved with a sensor inside our bloodstream that was able to directly feel blood chemistry, let's say along, 20 different parameters, like a super tongue kind of thing, right? If you had that ability to detect your own body physiology, I think our primary perception would have no problem feeling that we live in a 23-dimensional space, that our liver and our kidneys are intelligent agents that are navigating that space for us, right? Navigating that physiological space, solving problems, having memories and all of that. It's very hard for us to have an intuitive understanding of that. So what I think is really critical for many aspects of science and human flourishing, but also for AI, I think it's the biggest thing missing from the AI discussions today, is this emerging field of diverse intelligence. This idea that we ought to, if we really, in order to reach a mature understanding of cognition, intelligence, and so on, we need to be able to recognize it in very diverse substrates. So we're talking about beings that are synthetic, not necessarily evolved, or some combination thereof, right? We're talking about various kinds of swarms. We're talking about different kinds of software agents. I mean, all of these things, right? And this is a very old idea. Turing and long before that was this idea that intelligence is not bound to a specific physical substrate. It's about other things. And I particularly like the emphasis on problem solving, and I like William James's definition of intelligence as the ability to reach the same goal using different means. And that it's a very cybernetic definition. It doesn't say whether you were evolved or designed. It doesn't say what you're made of, what kind of brain you have. It just says in some space, there is a set of goals that you, with some level of competency, and that might be very low or very high, you are able to reach those goals despite all kinds of other things, right? And I sort of bring an extra emphasis on this, which is that I don't think these things are intrinsic or absolute. I think that all of this, so determination of agency, of goal directedness, is from the perspective of some observer, which may in fact be the system itself. So the system has to be able to recognize its own actions and its own agency and tell stories about itself. But multiple perspectives on any given system are possible. They're not all equally good, though. That's really important. That's the difference between this system and the critique of it, which often the way it's inappropriately critiqued is people say, well, you're gonna find a spirit under every rock. Basically, every rock is going to have hopes and dreams. And my point is, no, this only makes sense if it allows you as an observer to more effectively interact with that system. So to the extent that you've guessed correctly, what space is it working in? What are the goals? What are the competencies to reach those goals? That allows you to have a more fruitful interaction with it in terms of prediction, control. Maybe you get something out of it if you're relating to a high-level, high-agency system. And different observers could have different guesses on all of that, and then we get to find out who has the better interaction. So it's not everything goes. So that's the idea. I see it as intelligence as an interpretation frame of one observer onto some other system, and then we find out empirically how good is that frame.
And kind of bringing this into the AI discussion, I think the point that this immediately suggests then is, of course, you mentioned already substrate independence. And there's a lot of debate, I think, that kind of goes around about whether a machine-like system could actually be intelligent. And that's something that you pretty explicitly reject. I think that you've talked about the failure of the life versus machine distinction. And in AI today, I think that there seems to be more and more acceptance that at least text-based systems, for example, could exhibit what we perceive to be kind of intelligent behavior. But there continue to be debates about things like embodiment, like grounding, that seem to come up. And I know that you've addressed these in some of your other works as well, that kind of come down to a matter of, well, what is the environment that we're dealing with here? That just because embodiment is pretty important for some things that we sort of consider intelligence or understanding, that doesn't mean that this always looks like my 3D body in physical space, correct?
Yeah, I think embodiment is critical, but we have to be expansive and humble about what we consider to be an environment and what we consider to be a body. So this three-dimensional space through which we move as animals with muscles and brains is not the only game in town. That is not the only problem space in which various types of agents solve problems. There are transcriptional spaces, physiological spaces, anatomical morphospaces, linguistic spaces. There are many other spaces in which you can be embodied, have a life, have preferences, have goals, have competencies to navigate that space. This 3D space is not the only one. And so that's really important. And overall, I'll just say this machine versus life thing is it was never any good, this dichotomy, but it's especially bad now that we understand developmental biology, we understand evolution, we have some synthetic bioengineering going on. I made a flow chart that I use to take people through this, and it's very simple. And it starts off asking, at the beginning, it starts off asking whether you are some type of a cognitive system. Most people will say yes. And then it says, fine, and what about a paramecium? Right? What about a single cell organism? And so now you got a real problem because if you say no, the fact is that you came from a single cell. You were a single cell once. And so if you're going to say that a single cell doesn't have any of these things, but you do, then you owe a story about how and when you got them. And developmental biology gives absolutely no credence to some magical bright line that said, at this point you were physics here, and then over here you're a cognitive system. That doesn't exist. So that's a problem. If on the other hand, if you say that yes, the single cell has some basal form of intelligence, well, it's well described by the laws of physics and chemistry. Lots of molecular biologists treat it as various kinds of machines. So now now you don't believe in machines anymore. So there's as soon as you try to impose this binary categorization of life versus machine, you get into these unsolvable pseudo problems, because that isn't how nature doesn't obey these categories. So for me, it's all about a continuum, and it's all about what kind and how much. It's not these questions of, is it intelligent? Is it this? Is it that? Those, I don't think those are the right questions. The right question is, what's the problem space? What goals, if any, is it trying to accomplish? What are the competencies? And what does that mean for us in terms of the tools we're going to use to interact with it? Are you using this? Are you using a soldering iron? Are you using a reinforcement learning? Are you using something from cybernetics? Are you using psychotherapy, or so what are you using to interact with the system? And that's really what you need to know.
In one of your papers, you speak about many of the things you just said, but then also you sort of bring up this idea of, well, what are the conditions required for something to be a self, which is a really interesting kind of additional component here. And I think that on your picture, there, as you said, is a substrate independence, but then also a kind of fluidity of what it is to be a self. And this brings together a lot of different questions, I think. So being a self, as you say, at its core is just this ability to pursue goals, and the kind of demarcation line of what myself might be can look different from time to time on your picture. And so I'd love for you to describe maybe in more detail how you think about that fluidity of self, but then also what that says about kind of the stability. How does a self kind of persist over time, given all of that?
Yeah, that last one is a profound profound concept, a profound question, and I'm sure Adam will have some stuff to say about that too. But let's just talk about the very basics of being a self. I mean, one of the things that is true about, first of all, the one thing that's true about all intelligence is that we are all collective intelligences. So we are all made of parts. The real question is about scaling. How do our parts that also have various degrees of competencies give rise to emergent individuals? So none of us are this like indivisible diamond of intelligence. We're all sort of parts, made of parts. And so if that's the case, what becomes really important is to figure out what's in and what's out. In other words, where do you end and the outside world begins? Because if you're made of particulate matter, and there's going to be a border somewhere, so you need to figure out where you set the border. And the scale of where that border is, and I don't just mean it's a physical border. It has a lot to do with effective control. So the things that you want to consider as part of yourself are, perhaps this is one thing that's important. It's not the only thing. It's one thing that's important about being yourself, is figuring out a good model of what it is that you actually have control over. And so you can imagine now that's completely not obvious. You would think that, well, it's the genetics sets your sensors and effectors. You know what you are. That's actually not true. Biology has amazing amounts of plasticity. We could talk about what happens during embryogenesis, how we can subdivide embryonic blastoderms to get multiple selves out of one thing that most people look at and we call it an embryo. Is actually potentially any number of cells in there. And then you have this control issue. When babies are first born, they can execute certain actions that kind of sort of move their hands and legs with some degree of control. Also, they can make certain noises that then food appears in their mouth, and so that whole system, so me plus mom plus all this other stuff, like that's me. I got really good control over that. But over time, that gets refined, because then you find out that, well, my control over the legs and arms is getting better. Control over mom is getting worse, progressively worse over time, right? So my noises become less effective and so on. So you start to reinforce, like, okay, what do I actually have control over? What is a reasonable place to set this boundary between me and the outside world? So that's one set of things that happens. Another set of things that happens is that because you are made of independent agents, these being cells that have their own agendas in various spaces, that scale of the self can also change. And you think about a rat. The rat learns to press a lever and he gets a reward. So the thing is that there is no individual cell that had both of those experiences. So the lever is interacted with by the cells at the bottom of the feet. The intestinal cells get some sugar, but no individual cell had both experiences in order to have that association, that associative learning. So who owns the actual memory that the pressing of the lever causes the reward? Well, it's the rat. So what's the rat? The rat is this collective emergent being that requires a particular mechanism, this thing we call a cognitive glue, which happens to be bioelectrics, both in the brain and in morphospace, that allows for the emergence of a collective self that can be the owner of memories that the parts don't have. And that requires the parts to be joined in a very particular way. There are a set of policies about how these cells join up to be able to do this, partially through wiping individual memories and among the cells and some stuff like that. That's the part that is fluid, because during your life and during evolution, it changes. So if you think about the cognitive light cone, the size of the goals that these cells can pursue, individual cells, amoebas and such, have little tiny cognitive light cones because all their goals are at the single cell level. It's metabolic states, proliferation, the things like that. But when they come together, evolution did this amazing thing by giving us these scaling properties where now they can work on massive goals. For example, a salamander limb, the cells create the salamander limb. If you amputate it anywhere along the axis, they will work really hard to get back to that goal. When they reach it, they stop. Yeah? No individual cell knows how long a salamander limb is supposed to be, what the number of fingers, what is a finger, but the collective absolutely knows. And so that scale up, right? So in evolution, you get this massive scale up. The cognitive light cone not only gets bigger, but it also shifts into another space. It's now in morphospace, right? Whereas it used to be in, let's say, physiological space. But it can also shrink, and this is where we're going to get into, you wanted to talk about cancer at some point. It can also shrink, because individual cells that disconnect electrically from the network now are basically roll back to the cognitive light cone of a single cell. They, as far as they're concerned, the rest of the body is just external environment. So this idea of, where are my borders? Well, it depends how am I connected to everybody else informationally? Do we share the same goals? Do we share the same memories? Do we have the same compute power and so on? And if you don't, then you can have metastasis and transformation and all of these things. So this fluid, the size of the self, it changes during evolution and it changes during your lifetime, both during embryonic development and then aging and potentially cancer.
The multi-scale competency picture that you painted is a really important part of kind of everything here. And I think we'll get into this a little bit more when we come to specific details of your technological approach to Mind Everywhere. But one question I have about sort of how things happen at these multiple different levels is kind of an analog, I think, of the combination problem for panpsychism. And you do sort of talk about the ways in which your technological approach kind of implies something like a panpsychist view of consciousness. And here you're kind of looking at something analogous for cognitive function, where at the level of a cell, as you said, in a salamander, a cell doesn't know how long a salamander limb should be, but somehow collectively that knowledge seems to come about. And so I think we kind of had this analogous question here of, well, these smaller things, these individual cells, they only have goal directedness, they only have the ability to represent at their particular level. And so how does it emerge that a system that is composed of these things actually is able to represent these more complicated ideas?
Yeah, well, so the how does it emerge is actually that is a kind of what they call the easy problem in the sense. I mean, it's not easy at all, but it's a straightforward scientific enterprise. In other words, we and Adam will talk more about this. Like we are making models of how individual goal-seeking units can be linked together into collectives, and in fact, connectionist thought in both machine learning and neuroscience really gives lots of good. Well, at least we think we're good. Maybe there's better frameworks to come, but they give good ways to think about how you build a collective from active units that knows things that the individuals don't know. I mean, there's plenty of this in neural networks and so on. So there's plenty of ways to like that's a standard research program. The thing that I'll say about the panpsychism, and so I don't want to get too much into consciousness per se because I haven't really said too much about that yet, and so I'm still kind of working some stuff out for that. But there's I think it's important to keep in mind there's kind of two types of panpsychism. There's the kind of standard older kind, which is we're going to take regular old physics, which works perfectly well, and then we're going to paint some extra feelings onto the electrons, right? And just say that so that one. So nobody likes that kind. Well, some people do, but most people are down on that, and they kind of really reject that because they say, look, if your physics works perfectly well, don't be painting all this other stuff onto it. And in fact, and then of course the problem is if you don't, you have to do it at some point, or you end up in the eliminativist camp where it's just not there at all, and that gets into other problems. But there's a different way to think about it, which is the kind of, and other people have thought about this too, but it's the kind of stuff, the kind of research program that Carl Friste and Chris Fields and some other people are doing, where instead of painting cognitive properties onto a perfectly good physics, what they're trying to do is to recast basic physics as having elements of cognition from the bottom up. And again, this is something that Adam will talk about. But this idea, Carl calls it the physics of sentience and the sentience of physics. This idea that the kind of physics that we look at, this like very dumb mechanical interactionism, is really just a limiting case of a much more profound active inference process that is really there at the beginning. So the research program is to recast physics as we know it as fundamentally a cognitive process. And that, I think, is a very healthy form of panpsychism because it will fundamentally, remove these weird pseudo problems where you're like, well, we know we've got it at the end. We don't want it at the beginning. Where is it going to show up? And this is really unsolvable. But it does provide this kind of like very, assuming it can be, done. And this is obviously just the beginning of that project. It provides a very pleasing scenario where things that you already know, like basic physics and so on, fall out as a consequence of this much more fundamental way of thinking about things. I like that a lot. So that's what I like.
Before we get into regenerative medicine, I do want to discuss that in detail really soon. I want to touch on some of the ways that your thinking implies that we then think about AI. And I think we've kind of teased versions of this before, and how intelligence can exist in different substrates, can exist in different spaces. One of those spaces might look something like language. I want to ask specifically, though, at this very high level, there's a lot of questioning around what is the appropriate object, the thing that we want to build when it comes to what it is to be an AI system. What is the appropriate target for cognitive science, for instance? And Stefan Harnad, for instance, thinks a lot about this idea of grounding and what he terms T3, a robotic version of the Turing test, where your goal is not just to convince somebody over like a text game or a conversation that you're a human, but to actually exhibit all of the robotic capacities that a human being like you or me has. And presumably he's thinking about sort of the standard 3D space when it comes to where that competency is exhibited. But his sort of idea of what really constitutes true intelligence and understanding really is tied together with that idea that I have this sensory motor grounding in the physical world. I can interact with things. I can learn how to do things with the right things. And I think that there is an element of goal-directedness, of teleology in that. But your thinking seems to imply that maybe there's a lot more that we have to start thinking about when it comes to the idea of developing what we could really call human-like intelligences, as well as sort of expanding the space of what that looks like.
Yeah, I mean, there's a couple of things that I don't like in that whole framing, like, right. So one of them is that trying for a human brain. I mean, okay, it's fine that somebody wants to do that, but taking that particular goal as the kind of universal goal for artificial intelligence research strikes me as just completely wrong. Humans are one type of intelligence. intelligence has been around in biology and evolution long before neurons and brains came on the scene. And why? I mean, I sort of think about the wider universe. I kind of assume that there's all sorts of intelligence out there, and thinking that for some reason humans and the few tricks that we know how to do in 3-dimensional space is like the thing that you want to prove. Why that's the Turing test, I have no idea. That just doesn't seem, that seems so narrow to me. And I think, and also I when people say, it's not general AI because it doesn't do these things that human has, or it has different failure modes than humans have. I mean, that's fine. That's the whole point of intelligence broadly conceived. And I think Turing would have been on board with this. Is that there are many different ways to solve problems. They are not all the same. I think that we should be thinking about how do you convince somebody that you've got the intelligence of a liver. Right, that's not done in 3-dimensional space. That's done by cleverly navigating a physiological space and transcriptional space. And but I happen to think that we have so much more use for those kind of intelligences right now than things that we already have humans. We have plenty of humans. What we need is all kinds of other intelligences in other spaces that help us to really understand what we mean by intelligence broadly, that help us relate to other minds that are unconventional and that are not exactly like ours. I just think that that test is incredibly narrow, and I don't think that AI should be a model of how the human brain works. We have neuroscience for this, and it's fine. And when people say, "Well, that isn't at all how the brain does it," I mean, fine. The brain, how the brain does it, is not the only way that this is going to be done. So I think AI should be a lot more interesting than just trying to make models of the brain, and specifically of the human brain.
I think the picture you painted does look more interesting. And one of the things that we've kind of teased out a little bit that I want to dive into more is the implications and how some of the way that we think about intelligence here can manifest in regenerative medicine. So I'd love for maybe you two to introduce in a little bit more detail the work you've been doing recently together.
I'll jump in on this. So one of the key kind of insights that really captured my attention about Mike's work and the framework for it is this idea that there's intelligence at multiple scales, and that the types of spaces that even cells, for example, are navigating is meaningful, right? We have this story that because they're small, they're passive or they're uninteresting, right? That all of the behavior of cells could potentially be distilled down to, say, genes, but it can't. It just can't. And we know that more and more from the experiments that have come out of Mike's group. You can take, for example, cells that have all sorts of genetic mutations that are typically associated with cancer. But if you send different signals into those cells, or if you put them in different kind of communication configurations, then they will not progress in the same way as normal cancer cells, even though they have the genes for it. You can give cells all sorts of drugs, and you'll say, oh, if we give them this drug, then they're going to respond in this way. But then they don't because they start to learn, right? They start to become resistant or immune or whatever, right? We see this in antibiotic resistance and chemo resistance and all sorts of other drugs. So the idea that there's this sort of simplistic, passive input-output relationship between chemicals and behavior, or between genes and behavior, is just a framework that has been empirically disproven. That's not to say it's not true in individual cases or in instantaneous moments, right? Cells do have an instantaneous response to a gene or to a drug. But if you want to understand the dynamics over time, the progression of disease or the generation of limbs, you simply cannot distill that down to the activity of a few genes or a few proteins. You have to look at these interactive, dynamic informational networks. So once you adopt that lens, I mean, look, it took me years to come around on this, because like almost everyone, I was trained on the reductionist view. But once you start to look at that, it opens up a world of possibilities. And I'm going to sort of parallel something that Mike said earlier about breaking things down into smaller pieces. I think the way that the world has been explained historically in the West has been a group of people who say it can be broken down into the component parts. That's the sort of reductionist approach. And then maybe a more holistic approach, which is, well, it can't. There's these other effects, and you need to consider those other effects. and it's not so simple. And like, obviously, both are true in certain cases. What's been missing is the synthesis of those two to say, okay, if we can't break it down to genes and we can't break it down to proteins, we know that there's all these complex system level effects. Is there something that we can break it down to anyway? And the answer to that is yes, there is. You can break it down to flows of information. You can break it down to communication and decisions and goals. And that's not a woo concept. That's very quantifiable, very computationally tractable, and it makes very specific predictions in many more spaces than the pure genetic or the pure protein or the pure signaling approach would get you. So this idea of using information as the common currency, bits, entropy, and so on, for understanding the behaviors of interacting systems. I mean, in some ways, it's a throwback to the whole, start of the field of information theory. It's just that now we know we've had enough decades of accumulated evidence to say that biological systems are information processing systems. And so that now we get to borrow those tools and apply them to this area. So that's really the founding idea of Astonishing Labs, and the reason that I've been working with Mike and with Jess and with other folks on our team to bring these into human patients is because now we know enough to make good predictions about how cells will learn, and we can adjust those inputs so that the cells learn what we want, so that they get on the path towards, for example, healthier bodies, regenerative outcomes, less aging, less cancer, sort of all of those things without having to edit the genes. And that's the exciting part. You can use these other informational properties as an alternative or even as a complement for genes instead of just relying on the physical and genetic reductionism.
So the paper on future medicine that we were going to discuss a little bit, and I think to what you, Adam, said, there's a lot of really exciting implications there for things like regeneration. The idea that, say, a human being could actually regenerate a whole appendage or organ really does sound like something out of a superhero movie. I'm pretty sure that we see that in a lot of cases. And so really what you're kind of promising here and the approaches are, how can we make that kind of thing into a reality? I know that there do exist examples out there, for example, with salamanders. I know that Professor Levin, you've talked a lot about the rearranging of a frog's face as an example of sort of this kind of homeostasis that things bring into. But I'd love to make this a little bit more concrete in terms of what are examples out there of how this type of thing can occur. Maybe Adam, I don't know how much you can speak to some of the specific research you're doing and like results that you've had, for example.
Yeah, let me just make a preliminary statement around this, right? So all of this, like Mike was saying earlier, depends on the point of view that you take towards the question, right? It is preposterous that humans could fly until we had hot air balloons and airplanes, right? And then the answer is, oh, actually, we can if we have the right tools, right? If you say it's preposterous that humans can regenerate limbs, I mean, like, yeah, empirically, we haven't done it yet, mostly. I mean, Michael probably have a few examples where little infants can regenerate some stuff, but adult humans don't generally regenerate stuff. That's true. But if you ask the question, are humans capable of generating a liver? Are humans capable of generating a bladder? The answer is obviously yes, because we all did it. Otherwise, we wouldn't be here. Right? And when you look at it that way, then the question becomes a little more interesting. It's, okay, if instead of trying to solve the regeneration problem, we're simply trying to understand the generation problem, which our bodies have already solved, well, then that offers a completely different lens on the question, which I happen to think is much more tractable and something that we're going to crack probably in the next decade or two.
Yeah, this is a really good point. So oftentimes when I show the planaria, these flatworms, and you can chop them up into pieces, and each piece gives rise to a perfect worm, people say that the audience is that is amazing, wow. And I said, well, you guys know that half of you in the audience can regenerate an entire human body from one cell. You can literally regenerate an entire human body from one cell, because that is exactly what happens, and that's what Adam's talking about. And so we know that cells have the ability to make this stuff. Some of them tend not to, but some of them do. So deer, one of the examples I like, deer every year when they shed their antlers, they'll regenerate bone, vasculature, innervation, skin in exactly the right shape at a rate of 1.5 centimeters of new bone per day. So here's a large adult mammal that's able to regenerate some stuff. Human adults regenerate liver and so on. So we know it's doable. We know there are animals that do this. We know that we can do some of it. Here and here's, I think, the approach that we're going to take to this. For any kind of a system, you have to decide what the right level, what the right set of tools is, and a lot of that depends on how much cognitive capacity that system has. So I have this thing in the Tame paper called the axis of persuadability, and you could just imagine you have sort of mechanical clocks on one end, and then some homeostatic thermostats and things like that, and then some learning systems like animals and reinforcement learning agents, and then eventually some sort of high level metacognitive human like thing. So the key is that with all of these things, you have to figure out where your system lies on that spectrum to know what the right set of tools is. You don't want to spend your time trying to guilt the clock into doing something different. That isn't going to work. But also you don't want to treat an advanced learning agent as if it were a mechanical kind of thing, because you leave it all a lot on the table when you think that your only choice is to sort of micromanage it like a puppet, right? The reason that humans were able to train dogs and horses for thousands of years without knowing any neuroscience at all is because these systems offer this amazing interface, right? This learning interface. You don't have to know what's under the hood. You can sort of use this interface. So, okay. So you look at this spectrum and you ask yourself, well, where are cell collectives on this spectrum? And a lot of people have, in fact, in the kind of history of molecular medicine and developmental biology and so on, the assumption has been that they're way on the left. They're these mechanical things, and we need to rewire them, and genomic editing and CRISPR, and we're going to micromanage all this stuff. We're going to 3D print organs, and we're going to that's the level of control. And the thing is, what's key is that's an assumption. That isn't actually something for sure that's your best level. That's just the level people are often the most comfortable at in this field, chemistry. They often say that it's because it's they want to reduce down to the lowest level. But if you say so you want to work in quantum foam eventually, and they say no, that's crazy. It's chemistry is the way to go. So right. So it's not really reduction. It's really that just like people have picked this level of chemistry as what they like. But that's an assumption. And so the question is where is it? And so we've been working on this idea that actually cellular collectives are literally a kind of collective intelligence that solve problems in various spaces. One of the space you're working in is anatomical morphospace. It's the high dimensional space of all the different configurations that you might take. And then the question then it becomes a navigation problem. It becomes how does this swarm? And there are plenty of people who work on robot swarm navigation, right? And various types of vehicles, autonomous swarms of autonomous vehicles, and so on. It becomes a question of how does the collective navigate that space from where you are now, and that might be an embryonic state, it might be an injured state, whatever it is, to the position where you want to be, which is the correct target morphology for that animal or plant. And so the question is going to be, now you can reframe all of this into all of the tools of behavioral science. What are you measuring as that agent? What do you remember about your space? What are your prior expectations about that space? What are you willing to do? How much energy are you willing to spend to go around obstacles where temporarily your distance from your goal actually gets worse, but then eventually it will get better? Like how much delayed gratification can you muster? All of these things, and then some very specific things around active inference that Adam should talk about. These become the targets of interventions. And the cool thing about that, if that works, and we've been for years showing various examples of it, it has a very particular kind of power, which is this: the standard paradigm has genes are interacting with each other. They give rise to proteins. These things interact with each other according to local, fairly simple rules. And then through the process of emergence and complexity, out comes whatever, a salamander, a human, whatever it's going to be, right? So fundamentally that's a feed forward open loop process where you have parallel simple rules, and then you get this complex result at the end. So and that's fine, and all of those things do exist. But if that's the only way to do this, then you've got a serious problem, because figuring out how to make changes at the system level, so large scale changes, in order to do that, you need to understand what are the ways in which you're going to change those rules. And that is a horrible inverse problem that is fundamentally not solvable. So just if you think about fractals, right, these beautiful kind of very complex things, and they're generated by a tiny little rule. So, z squared plus c is your formula. And somebody says, oh, amazing. I love those 3 giant curlicues. Give me one with 4. And plus I want this other thing over here. How do you change the formula, right? They're not invertible. That's just not going to work. And so that limits everything that we can do with CRISPR, with synthetic biology, with protein engineering. That is the ceiling for all of those things. Instead, if what you actually have is a homeostatic problem-solving system that is able to recognize distance from its various goals and do certain things to get back there, then the game is completely different, because then what you can focus on is respecifying the goals, manipulating the system's expectations, beliefs, and measurements about where it is, and eventually augmenting its capacity to do a better job at what it already does. So that is the kind of stuff we've been doing.
Yeah, I did want to it was kind of interesting that you called out protein engineering, Professor Levin. I was curious to hear you talk a little bit more in detail about that, just because in AI right now, that's a very hot area, especially with AlphaFold, and some other researchers I've spoken to recently are very excited that now we have these generative AI systems that can, given maybe a goal you want to achieve or something of that sort, we're kind of getting in the direction where then you can generate a 3D molecular structure that is able to achieve it. And as you said, there are maybe limitations there, but it does seem like there's, at the very least, I can kind of describe declaratively like a goal I'd like to achieve. And then I, at the end of the day, have a 3D structure that is able to achieve it. And so there's something to the idea that there's problem solving going on there. But I think, as you said, there are limitations. And I'm curious just to hear you maybe riff a little bit more on how you think about that.
So this is a place in which I think it's really easy to get caught up in kind of a black and white thinking. What Mike and I are saying is not that proteins don't matter. Proteins obviously matter. And there's an amazing amount of insight that we're already getting, and we're going to continue to get, about how to navigate the space of protein folding. However, there's this implicit assumption that underlies much of biology, much of psychology, much of sociology, which is that if you just understand the proteins, then you've got it all figured out. And that's what we're saying is not warranted. So you can build the world's best protein folding computer, and you can build the better version than that and the better version than that, and it will still not allow you to end the war in Ukraine. It will still not allow you to reverse cancer once it's begun, because wars, cancer, all of these things are complex systems that are governed by the rules of the individual components and the interactions between the components. You need to understand the information flows, not just the building blocks, if you want to have a full account of the system. So I think this is the way to kind of, it's not even threading the needle. It's like the honest take, right? The honest take here is AI is doing a great job at helping us do reductionist science better. And that science is going to pay significant dividends for human health. But it is not likely to cure cancer, and it's not likely to reverse aging, or at least not to do them as well as it could be done, because cancer and aging are multifactorial, multi-scale information problems, not simply protein problems.
This is a really good way of putting it. I'd love to maybe speak in detail about a specific example of how regenerative medicine could look. And one thing that came up in the Future Medicine paper is the example of a clinical application in liver disease. And I think the specific term was hepatostat. Could either of you two maybe speak to that in a little bit of detail?
Yeah, and I'm certainly not an expert on that. So that's Eric Lagasse, who was my co-author on that paper. That's his expertise. But the bottom line is that they have this notion of need of function, which is that what they've been able to do is to realize that and I think this goes back to fairly old work that says that if there are certain functions, let's say the functions that the liver does, that if you have multiple pieces throughout the body, they will grow until their total effectiveness, their total physiological effectiveness reaches a particular point, and then they stop. So this idea that there's homeostasis in some kind of physiological space where the system can tell how well things are going and keep improving or keep increasing or keep growing or whatever it needs to do until that need is met. And so Eric pioneered this amazing thing where they implant pieces of liver in various other in lymph nodes and various other locations, and they show that it works, and they can rescue normal function and so on. So that's really important, right? It's this idea that the materials you're working with, and I call these things living tissue. Is an agential material. It has competencies. It has various things you can take advantage of, right? That you don't have to be there to micromanage every part of this, and that's really powerful. And I think Adam said a very important thing, which is that nobody's saying that that you don't need to understand your hardware, or that the focus on the kind of lower levels of this hierarchy isn't important. It's absolutely important, but it's the same reason we don't pick up a soldering iron nowadays when you want to go from Photoshop to PowerPoint on your laptop. It's that you can work at the hardware level, and many people do for specific things, but there's so much to be gained by understanding reprogrammability, by understanding the kind of competencies of your hardware. And no, it's not like a typical von Neumann architecture, of course not, but that aspect of reprogrammability and of having a computational substrate instead of like passive materials is going to be critical for biomedicine.
I think this is a really good set of things to kind of begin coming to a close on. And so I think that over the course of this, we sort of introduced a lot of different ideas that I imagine listeners might not be as familiar with when it comes to imagining the intelligence that goes on at different scales in the body. And so perhaps just because I want to bring the discussion back to AI, this being an AI podcast, I think a final kind of interesting question here might then be about, we've presented this pretty alternate view of what an intelligent system might look like, the spaces in which it might operate. And that necessarily expands our views about, well, I'm thinking about AI systems, about other sorts of systems. This changes what the idea of a machine is. For instance, in the Future Medicine paper, you actually talk about the idea of synthetic biologists viewing their medium as a machine, right? And sort of the idea that we can rationally understand these things, that they still do have intelligence and agency. I think a kind of final takeaway here would be, for AI people right now, this is just a very interesting, weird time where I think that many people's intuitions are being messed with in a pretty different way when it comes to the language systems that we're looking at right now. And I think that from a perspective of what is it to be intelligent, what makes intelligence, how do we think about things like moral patiency when it comes to the systems we might be building, that throws a lot of these things into question. And so I think for somebody listening to this who's kind of thinking about their role in building AI systems and dealing with them, what would you say to them in terms of somebody thinking about, well, I don't know how to reconsider some of the moral quandaries or the sort of recognition that comes along with what it is that I'm doing?
I think that a good place to start is to see what happens when you substitute the word computation for intelligence, or computational for intelligent. Not because they're necessarily the same, but because once you start looking at the world, and particularly biology, as a bunch of agents doing a bunch of computations, then it sort of tones down the rhetoric a little bit, right? So as Mike said, there's good reason to say that a paramecium is doing computation. It obviously is. There's good reason to believe that every cell in our body is doing computation all the time. Nonetheless, we don't generally feel too bad about what happens when a few of our skin cells die and fall off. We don't lose sleep over that because they're relatively simple intelligences or relatively simple goal-seeking agents. As they become more compound, then our moral concern goes up. And as they become very compound and they become very intelligent, capable of performing all sorts of computations, then those are humans. And then we start to become very concerned for their sort of fate. And I think that's all appropriate. If we're going to be more concerned about certain things than others, surely we should be more concerned about the things that have a greater capacity to feel or a greater capacity to experience different states. I think that all lines up. Insofar as computers are intelligent, and that's not to say they are today, but if at any point in the future they are, if they're built of multiple building blocks, each of which has its own sort of basal intelligence, which arguably we don't really do in AI today, but we could. There's some experiments in that direction. But as we start to build these compound intelligences, it's right for us to ask, so how intelligent are they? What are their preferences? Are their preferences being fulfilled? And what does that mean in terms of moral concern? But here's the catch, right? These aren't just evolving systems. We're building them. So we have the ability to engineer them in such a way that, for example, their goals are helpful to us as opposed to harmful to us. And so that they are satisfied when they do things that are helpful to us rather than harmful to us. So there isn't a conflict between what the AI wants and what we want because it's doing or it's even learning what we want. That's the analogy that I would draw to where we could go vis-a-vis us and our own skin cells. The reason we don't worry about our skin cells is because unless they're cancerous, they're on our team. What's good for us is generally good for them and vice versa. The reason that we do worry about AI, a lot of us, including me, is because we haven't yet figured out how to have it behave in a symbiotic way with us so that what's good for us is also good for it. Instead, we find ourselves constantly dealing with the opposite, where the AIs are pursuing goals that are clearly either ignorant or in outright opposition to ours. That's why it's so important to understand these multi-level information flows. Because once we can understand the dynamics of symbiosis, then it'll be trivial to build AIs that are our friends. But until we understand the dynamics of symbiosis, we're almost surely doomed to building AIs that not only work against us, but might even suffer while they work against us, which is the worst of all worlds for everyone.
I think this is a great message and note to end on. Adam, Professor Levin, thank you both so much for your time. And I really admire and appreciate the work that you both are doing together and individually. So thank you so much for speaking about this with me.
Cool. Thanks so much.
you.
Appreciate it. Yeah, thanks for having us.
And that is a wrap, my friends. As I mentioned at the start of the episode, you can subscribe to The Gradient on Substack to receive not just this podcast, but also our articles and newsletters directly to your email. You can also visit us at thegradient.pub, where you'll find all of that, as well as more information about The Gradient and how you could even contribute if you're interested. And finally, if you enjoyed this episode, we would really appreciate your feedback. If you'd like to leave a comment or review, we'd love to know how we can make this series more interesting and informative to you. And with all that, I'll leave you until the next episode.